This brief tutorial is designed to help you understand a little bit more about the grand challenge of making solar energy economical. In particular, what I want to do is describe how much solar energy is available, ways that solar energy can be used, how photovoltaic energy works, and some of the issues of materials and conversion efficiencies, and then finally to understand on the economical side what the actual costs are. So this is designed to be complementary to what Dr. Sampath will be covering during class and give you a better idea of things to be watching for. In particular, as you go through this presentation, be watching for the units and the amounts that are being used so that you can follow more clearly when he talks about the various technologies and where they are and where they're going. So let's start by talking about how much solar energy is available. As you remember from previous classes, the amount of solar energy radiance that comes to the Earth is around 1360 watts per square meter, or 1.36 kilowatts per square meter at the top of the atmosphere. Now, because of cloud cover and because of solar angles at the beginning and the end of the day, the amount of sun that actually reaches the Earth at any particular point will vary significantly. So what you're seeing here is an analysis that was done by the National Renewable Energy Laboratory, which is located in Golden, Colorado. And for the year 2012, they actually measured in those little graphs that you see how much solar energy actually reached the ground there. And you can see that their maximum scale is 1370 watts per square meter, so that's the same kind of flux that there would be at the top of the atmosphere. And you can see that the peaks are typically at the middle of the day, but there are cloudy days. Winter is not nearly as good as summer, and there are all kinds of other factors that play a role as well. So when you do that, and you do that analysis, you can actually plot how much solar energy is available at any place in the world. And this map basically shows that. And it shows you, based on those kinds of estimates of cloud cover and everything else, what the estimated total amount of kilowatt hours per square meter would be per day. That's the scale that you see at the bottom. Or if you multiply that by the number of days in a year, so 365.25, if you want to be really specific, you can also get annual numbers and what that looks like. And what you see from here is that the areas that have the most solar irradiance are the places that have the least clouds and that are closest to the equator. So basically, these are the major deserts around the world because they have less clouds. So now, having seen that map, and based on what I've said, which country do you think has the highest per capita solar energy production? Give that a thought. I would recommend that you pause for a second or go back and look at the previous map, and then identify what your conclusion is. When you're ready to continue, let me show you the answer. The answer is not what you expect. The country with the highest per capita solar energy production is Germany. Why is that the case? Because for the last 10 years, most of the solar panels are put into places where there are the biggest subsidies, and Germany has the biggest subsidies. Okay, so that's kind of an odd one. Now let's just go look within a country. And in this particular case, why don't we look at the US? And what I want you to note here is this is showing the annual amount of solar energy that's available in terms of kilowatt hours per square meter per year. And what you can see is that the deserts in the southwest of the US will give you about twice as much solar energy as the green areas, which would be places like northern Maine, northern Minnesota, and especially when you get to the Pacific Northwest where it's particularly cloudy. So that's why you'll see most of the solar farms in the US, these big areas, are going to be in the redder areas of the country. And that makes a lot of sense because you get more value for it that way. And you'll also see that Colorado in the Front Range is not a bad place for solar panels either. So That's talking about solar irradiance when it finally gets to the ground. But it's worth pointing out that solar could be used in a lot of different ways. The simplest and easiest is for lighting. And what I mean by that is windows. If you have windows in a building, like if you look at the Scott building, it uses a lot less interior light because of the way in which the windows have been built and the atrium has been built. So that is one of the most cost-effective things to do with solar energy. The next one is heating. That's very simple also. So if you have a glass pane and you paint things behind it black, those surfaces will get warm. And as we know, just like from the greenhouse effect in the atmosphere, the glass pane won't allow the heat to actually escape. So that works very well also. And that's 30, 40 years ago, that's the way a lot of systems were built. And you can still see hot showers or hot water heaters like that on roofs in various places. The primary thing we now think of is photovoltaic, which is where you turn the solar energy into electricity. We'll be talking more about that shortly. You can also use solar energy to produce biomass, so basically by growing plants. Solar energy also creates weather. That weather can create wind. And so when you have wind turbines, that's another way to get energy that indirectly came from the sun. And even more indirectly, that weather can create clouds, evaporate water, and then that can be dumped somewhere else. And so hydropower is also an indirect way that we use solar energy. So next, let's focus a bit more specifically on photovoltaics now and talk about how solar panels work. So you have in this module, you have a video that I recommend that you go through. And here are a couple of things that I would highlight as you think about this. We've seen this curve, I think, once before in class, and it shows that the amount of solar energy that's available at the top of the atmosphere and down at the Earth's surface depends a lot on what materials, the wavelength of the light that's coming through. Now, what I also want to point out is that the lower wavelengths, which is kind of in the ultraviolet, those parts of the spectrum have more energy for every photon. And that's explained by the equations that you see here, where it says the energy in electron volts is equal to 1240 divided by the wavelength in nanometers. So you don't really need to understand that physics now. You might see it in other classes as you go along. But the point is that the higher energy waves are closer to the ultraviolet side of the spectrum. So let's just basically show you in general again how photovoltaic energy works. So you have a semiconductor. That semiconductor works with a light source, i.e. the sun. The semiconductor consists of two different types of silicon. In this case, if we're doing a silicon type system, you have the N-type silicon, which has too many electrons, and the P-type silicon that has too few electrons and therefore an excess of holes. Light from the sun, if it is low energy light, passes straight through, and then when you finally get to energy of the right wavelengths, that energy of the right wavelengths is what gets absorbed at the boundary and converted into what I'll show you here in a second. But there's also energy that doesn't quite get there, and there's also photons that reflect off the front surface. But it is path C that is most significant. And what path C does is it knocks electrons free, so the electrons are then able to go in one direction, the holes go in another direction, which then creates electrical potential that can then create current, which you see. There are electrodes on the front and there are electrodes on the back that actually connect and pick up those holes and those electrons. The current flow is usually shown going from plus to minus, but in reality the electrons are actually negative and they flow in the opposite direction. You don't need to understand all of this in great detail, but I just wanted to share it with you because if you did get into the world of making photovoltaics, this kind of physics is where you would start. Here is more detail of the boundary layer between the N and the P-type. The reason that I've included this, this is for silicon-based systems, but what I want to point out is that for other systems, for example, the cadmium telluride that we'll be talking about, that Dr. Sampath will be talking about, the interface between those two, that depletion zone that is marked there on the far left, is the most important part of the whole system in terms of having a system that is efficient. So let's talk about efficiency, and let's talk about the different kinds of materials that can be used for photovoltaics. Here is a list of some of these types of materials. The one that we typically think of is silicon. For even higher efficiency at a higher cost, there is gallium arsenide. It is also a semiconductor, works very similar to silicon. The type of materials that are being developed here at CSU is cadmium telluride. Dr. Sampath will talk a lot more about that. There are other compositions also of what's called thin film. There are perovskites. There is a combination of copper, indium, gallium selenide, usually abbreviated as SIGs, and there's many other possibilities, and it's also possible to combine some of these, which is where the field is really going at this point. To show you where the field is going, what I have for you here is basically the last 55 years of solar photovoltaic development. And you can see different technologies. They're marked by the different circles and squares and triangles that are indicated in the upper left. And then you can see for each of those technologies the kind of efficiencies that they've been able to generate. And you can see that that goes as high as 47.1%. But what I want to caution you to is that the types of materials that are used for over 30% efficient solar panels currently, those are super expensive, and they're not practical for use in a common type of commercial installation. Instead, let's focus on the technologies that are in the lower right, and here you can see these in greater details. Cadmium telluride is a green circle that has yellow inside of it, and that is the technology that's been developed at CSU, and you can see how between 2010 and currently how much that has improved. There are other technologies that are also on the way up, and in particular you'll see that the highest versions of the various technologies, like for example the one that's labeled at 29.5%, is actually 2 layers of 2 different materials. So it has silicon as well as a perovskite. So there's more and more things that are going on with multi-layer, and Dr. Sampath will talk about that also in his presentation. Let's talk about cost. In general, there's something called Swanson's law, which says that the more you produce of something, the more experience you have, and the more that the cost goes down. And you can see this just as between 1976 and 2014, what happened in terms of the cost of solar panels. The scale on the vertical axis is logarithmic, and the scale on the horizontal axis is logarithmic as well. And so you can see more than 100-to-1 reduction in terms of the cost between 1976 and 2014. And we'll talk a little bit more about closer to the present as well. So here we are seeing some of the technologies that have brought down the cost of silicon photovoltaics and where that has gone. And what you also see here is the installed cost of electricity. So remember that in class we've talked about 12 cents per kilowatt hour as being the retail price, and around 3 cents per kilowatt hour being the wholesale price. Actually, this is showing a wholesale price of around 6 cents per kilowatt hour. It all depends a little bit on how you measure these different things, but we're looking at the same types of numbers here. Now, another way to think about that is, what does it actually cost for a solar panel to install everything? So we normally think of just the solar panel. That's in red here, and it's the module. And that's about 65 cents out of the $3.25 total if you were to put solar panels on the roof of your house. So this is for a residential photovoltaic system, and what you can see is that the electronics cost more than the module. You also have to install all of this on the roof, and you have to find a company that does that, and they have to survive. So that's why you're seeing this multiplier of about 5 times from the module cost to the cost of the entire system before it's running and usable. That's if you have solar panels on the roof of your house. That's called a residential system. When you see these big fields, those are called utility scale photovoltaic systems, and those systems cost less. So the module costs about the same, but there's all the other costs are shared over a much larger field of these, and you can see that that cost drops pretty significantly. And you're seeing $1.80 per watt of peak power here, and this is based in 2014. What I next want to show you is that those costs are continuing to come down, so that for this utility scale, it's actually down below $1 now by 2020, and for the residential, it's down to somewhere around $2.70. But in particular, notice how fast the utility scale photovoltaics have gone down, and that's what's driving a lot of the installations and a lot of the ways in which solar technology is developing. So that's all I wanted to share with you. I hope you've enjoyed this presentation, and I think this will help you understand more when Dr. Sampath presents also.